This is second part of the chapter, the basic review of probability theory. Today we will cover these topics. Our today's content are Gaussian random variables, joint and conditional Gaussian random variables, then mixture probability density function, chi-square distributed random variable, then there are some process noise like random process, uh, random walk, linear process, Markov process, random sequences, Markov sequences, and Markov chain. Gaussian random variables. Uh, as we already discussed about the probability density function of a random variable in the previous class. So now what is Gaussian random variables? Gaussian random variables has a normal distribution which have some argument like scalar random variable x, and x argument has mean and variance. So now what is the PDF of Gaussian random variable, which is actually our periodic distribution. So P of x, our periodic distribution P of x equals to Gaussian normal. This notation is known as Gaussian normal distribution, having the argument x and mean and variance is equals to this. This is we can say density measurement or measurement density. So, and these mean and variance are our statistics that we calculate when we talk about the tracking system. Then we have to calculate the state x, like suppose this is the object state having a random value. So we will calculate its statistic like mean and variance in every scan. Then we apply normal distribution to update our periodic distribution, or to calculate to calculate the periodic distribution. Then we will apply Bayes theorem to update this periodic distribution and obtaining a posteriori distribution. So this will obtain using the Bayes theorem. So this is formula for periodic distribution for any Gaussian random variable like x. So in this argument, this x minus mean means, suppose this mean statistics we have calculated using some algorithm, like we apply Kalman filter, and using the Kalman filter we obtain the mean value of the random variable x. Then we calculate what is difference between the original value of the random variable and minus this is the mean value that we have calculated using some algorithm like Kalman filter, and this is divided by variance and having exponential function. Okay, because this is a complex mathematical problem. So another notation equivalent to above equation, like x is approximately equals to normal of mean and variance. This is just notation, like p of x equals to normal of mean and variance and equals to this density measurement. So which state that x is normally distributed the corresponding mean and variance. Now in case of vector valued Gaussian random variable has a density of this one. Suppose we have a complete vector. So this have this and this have some difference. This is just for a single value. Now suppose we are calculating the suppose we have given a vector of a random variable. Okay, so for the vector here, x is a vector, and then we calculate the mean and its covariance, which will equals to 1 upon root of 2 pi p. This is same as this one. We just replace this sigma with p and this sigma with p, and then exponential of 1 over 2, like this, 1 over 2, and into this transpose of the difference in mean and the argument, the given argument, and this transpose of mean and given argument into covariance, inverse of covariance, into the difference of mean and the argument x. So this is formula for vector valued. So this is widely used in tracking system to calculate the uh, measurement density in the, or you can say this formula also uses a likelihood of the measurement in the tracking system, where the x dash is the mean and covariance is mean value of the transpose of this value and this value. These are mean and covariance matrix for vector x. This is suppose the object is state or target is state x. The components of Gaussian distributed vector are said to be jointly Gaussian. So if covariance matrix P is diagonal, then P and X are independent because the adjoint PDF equals the product of their marginal. Suppose they are independent, then we use intersection of P and X. So in the P and X intersection, they are independent and they are equals to the product of their marginals, means that their respective probability. Okay, so like probability of P intersection X, or probability of P comma X equals to probability of X into probability of P. Okay, individual product of the probability. So a very important property of Gaussian random variables is that they stay Gaussian under linear transformation. If we apply some linear transformation, or we apply some transformation theorem between the vector variable, then they still stay Gaussian, and the sum of jointly Gaussian random variables is also a Gaussian. This property is a major reason that the Gaussian model is very commonly used in estimation. So this is example of two random vectors of the same dimension, like x1 and x2. Suppose we are doing some jointly Gaussian distributed. So jointly Gaussian distributed involve two or many random variables or random vectors. So suppose we apply jointly Gaussian distribution between x1 and x2. So x1 and x2 are jointly mixed together or jointly distributed using the Gaussian normal. So that is suppose this P is periodic distribution or PDF of two joint variables, and x1 and x2 equals to normal Gaussian into uh, the argument that we are talking about, x1 and x2, and its mean x1 dash and x2 dash and their covariance. So this covariance has some metrics because we are we are applying jointly distribution. So p11 and p22 p21, because we have a two vector random variable, then the covariance must be 2 by 2 matrix, and then our argument involve x1 and plus x2. So this is the Gaussian. X1 plus x2 is a Gaussian. P of x equals to normal x dash and p. So suppose in this x s equals to x1 and x2, x1 plus x2, and this means x1 dash and x2, and this p is a vector, sorry, matrix. P is also a matrix, and x dash is a vector, and x is a vector, where x dash is equals to x1 dash plus x2 dash, and p is a matrix. So symbolically we can write above equation as like this one. So this is the same thing, and that I have already written in above equation. Now again we take this same equation here. So this same equation, if x1 and x2 are independent, the PDF of their sum x1 plus x2 condition on x1 is, because in jointly we uh, uh, will first find the PDF of one random variable and then the other. So this is um, suppose we already know the x1 value. So the conditional probability of our argument, which is condition on x1, which means we already have data of x1. Now we are finding the PDF of x based on condition on x1 equals to px2 of x minus x1. So in this function p of x2, we just find the difference between the argument x and the x1. So equals to normal value of x minus x1 and its mean x2 dash and the covariance p22. So again the covariance is a diagonal matrix. So when we find the uh, p of x condition on x2, then this will replace the subscript on the each x will be replaced. Okay, like for example p of x condition on x2, suppose here test x2, then we will write here px1 into x minus x2. Okay, so it means if we find if we are finding x2 and we know x1, then we do like this one. And if we find x1 and x2 is known to us, then we place here x oblique or condition on x2 and px1 into px2 px1 of x minus x2. Okay, so suppose here we are taking x1, so normal of x minus x1 and x2 mean and p22, and this is same formula, all same like previous, but here our argument involve two random vector x1 and x2. So here x minus x1, this argument, that because our argument is equals to the function of the difference in x minus x1. So here we put the x minus x1 and minus x2 mean, and this is same and this is same, this is transpose and this is same, and this will equal to a normal of x1 plus x2 and p22. Note that in above solution x1 x is a constant, it shifts the mean since it is given in the condition mean. And similarly, if we put here x2, then here x1, then here x2, and here x2, then here x1 mean, and here p1 1, because it's diagonal matrix, and similarly here 1 1. So and similarly here x minus x2 minus x1 mean, So similarly, this find one joint vector, and given the other joint vector, we can find the periodic distribution of the multiple or jointly multiple random vectors. Now, joint and conditional Gaussian random variables. Okay, note that the previous lecture and the today's lecture are very important, and we will apply all these content or all these knowledge in the object tracking system. So this review basically is very useful for upcoming lectures. Now, joint and conditional Gaussian random variables. Two random vectors x and z are jointly Gaussian if the stacked vector is this one. Suppose y equals to x and z, where x and z are two random vectors, is a Gaussian, that is p x comma z equals to p of y and normal of y, where y is the same thing vector and this y mean and p y y. Okay, so our argument is y. Okay, so we are taking the covariance y y. Okay, so here the vector argument is x and z, and similarly what will be the y bar is equals to mean of x and mean of z. Okay, so this is a mean and covariance of y in terms of those of x and z, and similarly p y y equals to the pxs xz and zx zz. This is a 2 by 2 matrix, and the covariance of x and covariance of z, and similarly pxz the cross covariance equals to this one, and similarly this will equals to transpose of p zx. Now here we are finding the PDF of equation, the conditional PDF of x given z when they are jointly Gaussian. This one means you have given z, now you have to find the PDF of x using z equals to p of x comma z divided by p of z. Now this will equals to same formula we have to apply, because these are vector random, so we apply this like this one. This is 1 upon root over 2 pi p y y into exponential of minus 1 upon 2, the difference between mean and argument, and covariance and mean and argument. Here transpose, and here the same, and divide by the same thing, because p of z equals to this thing, and p of x comma z is equals to this thing. Mixture probability density function. So the mixture probability density function or mixture PDF is a weighted sum of PDF with weights summing up to unity. A Gaussian mixture is a PDF consisting of weighted sum of Gaussian densities, means it will add up. It will add up the all PDF and check whether it is normalized or not. If the sum of the all PDF equals to 1, it means it is normalized. And suppose p of x, the PDF of random variable x equals to sum of suppose there are n values in vector x, so j1 to n has a normal distribution of argument and mean and covariance, and this is PDF. We are adding up all PDF with some weight. Okay, so PDF mixture is a weighted sum of PDF with the weights summing up to unity. So where this P of j Pj is equals to 1. So Pj equals to 1, and this is a normal distribution of the vector and mean and covariance. Suppose denote by Aj the event that x is Gaussian distributed with mean xj mean and covariance Pj, that is Aj equals to x, which describe you Gaussian distribution. X has a Gaussian distribution of mean and covariance. So your Aj equals having these value j1 to n, and having a Gaussian distribution between the mean and covariance. So where the Aj are mutually exclusive and exhaustive, and the probability of Aj equals to Pj. It means out of these value only one value will occur. In other words, we can say that only one probability will be selected or will be a true probability, and same or same value cannot be happen together. Same thing cannot be happen together. So these Aj is mutually exclusive and exhaustive, and this probability equals to Pj. So if we uh, add up all probability, it must equals to 1. We can write the equation 3 with a total probability theorem as this one. The total probability theorem states that the conditional probability of x given the probability of the object state, this is any event, the conditional probability of the random value, condition on the probability condition on the event a into the probability of the event a. So this is a total probability theorem. You can write equation 3, this 3 equation 3, we can write this 3 using the total probability theorem. So this is again, this is a weighted sum of the PDF of x. Okay, so like this one, this is again the same, and it is this P of Aj is like this one. P of Aj is like this one Pj. We are adding up all PDFs which must equals to 1 here, and this is the conditional probability from total probability theorem. Now the moments of a mixture. Now what is mixture PDF? Actually mixture, we are mixing up the mean and covariance of the PDF. Here mixture means we are adding up or mixing up yeah, or you can say in simple word, we are adding up the mean and covariance of the PDF of a random vector. So here the mean of a mixture PDF is defined by the weighted sum of the means of the component densities as expressed by phi. So our mean value equals to sum of the Pj and the mean value, where Pj is what? Pj is this thing, probability of Aj, Pj is the probability of Aj, where this one is a negatively exclusive, exhaustive. So this thing and the mean value. Okay, so Pj is a weighted sum of PDF, and this is calculated using some algorithm like gamma filter. So gamma filter find the uh, object state vector at each time j, where j is 1 to n. So some algorithm apply some mathematics like gamma filter to calculate the object state mean value of the argument x. Then we have to sum up with the product of the probability of the event, and that event belongs to the object state. So event A is you have already known the event. You are finding the periodic distribution of x using based on condition on aj. So this is already known. You have some event j, and now you have finding p of x. So this thing is a probability or weighted probability, and this thing is calculated by the algorithm. Now the covariance of this matrix is given by this thing, the sum of all j and to uh, the e of mean of the difference between this thing and the transport of the difference between this thing, and this is a condition on aj. So this whole argument transport of this thing and this thing is condition on the event. Okay, so this mean is multiplied with the uh, pj. So pj is the same thing here, pj here pj. So pj is this thing, and this will equals, if we multiply the argument and apply the summation, then this will obtain. So equation 6 can be rewritten as in the 7 like this one. So this thing is a summation of 1 to n pj, the PDF of the j and the probability of the j plus p. Here's some, you can say uh, uh, estimated value of the covariance, and so this thing. So p uh, and p, this sign is called ascent. P of ascent is a spread of the mean from like this one. Okay, we just replace this argument with the p. Okay, so equation 6 and 7 are same, don't confuse. We just replace this thing with the p. Okay, so an alternative method is like this one. Okay, so if we multiply here, if we solve here and multiply and separate here, so we will obtain final equation often will be like this one, which will yield the things like okay. So so which will yield another form of equation number 7 like this one. Okay, so this state the sum of the PDF and the probability of j plus and this thing and minus this thing. Okay, so this is same thing. Here we actually solve the brackets, the arguments in the brackets we have multiplied, and separate this thing x bar and x bar transposed. We separate this part. Okay, so here this part and this sum we have separated, because this thing is already calculated in 5. Okay, this thing is already calculated in 5. X sum of xz into xz bar, xz mean of xz and pz is already calculated. So we will not calculate again. Here you can see that the x bar, sorry, xj and xj, uh, and x is also sum of the, okay, is also a vector. But we are, when we solve this equation, you will obtain like this thing, but uh, we uh, we already calculate this value here, so we just take the total value of the mean and put directly here. So here this there is a no summation, there is no summation, here summation, here summation. Okay, but here no summation because we have already calculated here value. So equation 6 to 8, like the 6 to 8, equation 5, equation 5 to 8 means a mean and 8. So you can either use this thing 5 and 8. Okay, because this uh, 7 and this equation and this equation are same. You can use anything, you can use this one, this one, this one, this one, or this one, like anything. So this is another form, and normally I used this formula in the tracking system in my algorithm, and these equations are widely used for object tracking estimation, which will calculate your mean value of the argument and its covariance. Okay, so mean value of the object state will be calculated by this equation number 5, and the covariance of the object state will be calculated by equation number 8. So this sum of Gaussian mixture PDF. Okay, we already calculated the PDF for all object state for all j's. J, you can say is a scan, one scan, two scan, three scan. Suppose the target is moving for 80 seconds, then j starts from 1 and n equals to 80. So we first calculate the object state and covariance, means xj and pj for every scan individually. Okay, um, and I you can say I j is you can assume that j is a measurement. Okay, so measurement of the object state, so we calculate the object state based on measurement, and measurement can be received from the sensor. So based on sensor measurement we calculate the mean and covariance of the event a. So a event is related to the object state, and we then use this formula to sum up the Gaussian mixture PDF to obtain the state estimate and the final output statistics. Now, approximation of a mixture PDF can be approximated by a single Gaussian PDF with moments by 5 and 8. Okay, so why do we approximate by a single Gaussian PDF? Because otherwise there are j values. Okay, we are j values, so it will be difficult to propagate j values of the object state to the next time scan. Okay, to the next time scan it will be difficult to propagate the object value. So uh, we just approximate to a single Gaussian variable with the use of 5 and 8. Here 5 and 8. Okay, so if we do not use 5 and 8, then it will be difficult to propagate j values of the mean and the covariance to the next time scale. So we just mix up the PDF and obtain a single Gaussian PDF, and this is called the moment matching. So in this case, this is example, the exact Gaussian mixture PDF. So we must verify that the exact match between the Gaussian mixture PDF and the corresponding moment match Gaussian mixture PDF. If it is not matched, it means that this sum up is not equals to 1. If the sum of the probability of all event equals to 1, then it will definitely match with the your Gaussian mixture. And so we must check the corresponding moment Gaussian mixture with the what does it mean corresponding moment matching? It means this thing, equation number 5 and 8. Corresponding moment matching, this the moment matching that we calculated using 5 and 8. Okay, this is the single PDF. This is a single PDF which we approximate using 5 and 8, and this is a exact known mixture PDF of the argument x, or Gaussian mixture of the random variable x. So this is the mixture PDF or Gaussian PDF of the argument x. Now suppose uh, we are calculating for the mean x1 equals to 15 and x2 is 20. Suppose x1 is 15 and x2 20, and variance are both the variance and same value 10. Now we can say that the solid line exactly matched with the dash line. So dash line is calculated by the 5 and 8 in both figures. So here P1 is the probability, like this one, 0.1, and P here in this case P1 is the probability of the 0.5. So here P1 and P2 is suppose the probability of 0.5, and this bar is the PDF. This bar is a PDF. Okay, and this P1 is a probability, like this one. This one, probability of the event j. This thing, the probability of the event j. Suppose Pj, P1 is 0.5 and P1 is 0.1 and P2 is 0.9, and here P1 is 0.5 and P2 is 0.5. So this is the PDF value of x given the event A. So this is P of conditional probability, conditional PDF. This is a conditional PDF of P of x, condition on A event. Okay, this thing, P of x, condition of A event. So P of x variable, condition on 0.1 variable, 0.1 probability and 0.2 probability, here this value. So this is we obtained the exact match. So figure 1 and 2, the figure 1 and this figure 2 represent comparison between the exact PDF of Gaussian mixtures and the corresponding moment match Gaussian for several values of parameters entering into the mixture. So in above figure, the resulting umbrella, like this figure like umbrella, Gaussian appears to be close to the exact PDF of the mixture as long as its components are not too far apart. Namely, the distance between the mean of the component is up to about two standard deviations. What does it mean? Because we in this thing we are calculating the distance between argument and x dash, like this thing we are actually calculating here. What we are calculating this thing, the x and minus x dash. Okay, so distance between these two should be not too far. If it is too far, then this thing happen. Okay, so uh, this Gaussian appears to be close to the Gaussian PDF of the random variable x, and so appears to be close to the exact PDF of the mixture as long as its components like mean and covariance are not too far apart. Okay, namely the distance between the means of the component is up to about two standard deviations. This approximate condition is met for the case depicted in figure 1 where the match appears good, and it is not met for the case in figure 2 where the match does not appear good. In figure 2, difference of the mean is 10. In both cases, figures uh, the the common standard deviation of the mixture is root of 10. So here you can say that the our Gaussian mixture of solid line did this thing, and the corresponding moment match is very far, like the dashed line here, and the solid line is very far. This is the not exact match. Okay, the reason that the distance between the components like mean and covariance are located too far away. So again, the these results are used in obtaining recursive filtering algorithm for systems with hybrid uncertainties. Hybrid uncertainties we already discussed in lecture 1. Means there are a lot of problems in filtering algorithms. So these results are used in obtaining the estimation for the recursive filtering. System falling into this category are those described by multiple models or with measurement of uncertain origin. Now, chi-square distributed random variables. So I hope you have understand this lecture mixture PDF. Okay, if you have any problem, you can come to my office next week, and these things will be repeatedly used in upcoming lectures. If the here what is chi-square? You can say the chi-square q is any threshold or any scalar uh, variable or threshold. This threshold is used to testing the distance of the variable x and its mean. Okay, so when we use this thing, because suppose the probability of the track of any type. Suppose we are tracking the object, so suppose two tracks following the same object. Okay, suppose two tracks following the same object, and both tracks have highest probability of existence. That probability of these tracks, it means that both tracks are confirmed. Okay, both tracks are confirmed that it is already know the event A of the object state, and both are correctly following. So now we will select only one, because there is one target. So why two tracks utilized to follow the same target? Okay, so we will just select one of the track. So how we do select? We just compare the distance, which track is closer to that target, which track is closer to that target. So if track 1 following the target has a smaller distance with deviation, and then the other, then that track will be selected for the output statistics. So again, this equation is very important. We used in every tracking system, because in tracking system, when the tracks are initialized for estimation, then many tracks follow the same target. Okay, so we this will take uh, a time. This will take some calculation resources, so we just uh, ignore we just ignore all tracks and select only one track which is closer to the x variable or the object state, which is closer to the object state. We will select only the one track, and this track will be used as a confirmed true track. True track means the object track. Okay, so suppose uh, if the n-dimensional random vector x is Gaussian with mean value and the covariance p, then the scalar random variable defined by the quadratic form, this one, which can be shown to be the sum of the squares of n independent zero mean and the unity variance Gaussian random variables. Such a random variable is said to have a chi-square distribution with n degree of freedom. So why we called a chi-square? Okay, so this can be verified by this thing. Let u is a Gaussian with zero mean and unity variance. So suppose u is the inverse root of covariance and the distance between the variable and its mean, and then it has suppose zero mean and the unity variance. So if we solve the covariance of the this variable u, then it will be equals to identity matrix. This will equal to p inverse of root of covariance and inverse of the root of covariance in p. This will equal to identity matrix. Therefore, since covariance matrix of u is diagonal, its components are uncorrelated, and in view of the fact that they are jointly Gaussian, they are also independent. Thus, following the equation number 9, we have this thing: q is equal to u and u transpose and u equals to sum of ui square, like this one. This thing where u is the p into x minus x bar. So here we just replace u and p minus 1. So here q equals to u transpose into u into sum of, equals to sum of this thing, where q is a chi-square distributed with n degree of freedom, which can be rewritten as this one: chi. This sign is known as chi. So we can say this another notation to known as chi-square. The q is equals to chi-square with zero mean and unity variance. Here we derived zero mean and the uh, unity variance. So q, how do you select the q? Q is as I already mentioned that it is a threshold for selecting the one of the confirmed true track from among the many tracks. So threshold is depend on the false alarm of chi-square. So the value is depend on the false alarm, objective false alarm of chi-square distribution. So it also depends on the on the velocity. So based on the velocity, for example, the target moves with constant velocity of 25 meter per second, then we select q equals to 10. Okay, and we use to select two value, for example 2 equals to 20 and q equals to 10. So suppose if the q equals to 10, then the distance between the mean value of x and the variable x is too far. Oh sorry, if the q is greater than 20, then the distance between the mean value and the x is too far, means it's very far from the actual trajectory of the object state. Then it will be known as a confirmed false track. Means false track, it is following some collector value or some other things because it is very far and the distance is greater than 20 value. And if it is a lie, if it is in less than 20 value, then it is closer to the object state. Then that mean will be selected for the output and will be used as a confirmed true track. The chi-square distribution q is typically used to develop hypothesis test. Okay, so suppose there are many hypothesis tests, then q will be used to select one of the hypothesis, because among the many hypotheses, only one hypothesis will be correct. So this is widely used in the Bayesian filtering and tracking system to select the closest hypothesis required for obtaining the estimation statistics and the results. So now random process. What is a random process? Means here we are talking about here we will talk about random and some stationary process. We must know there are some random noises in the Gaussian PDF. The random variable is a function of x of e that actually map the set of experiment outcomes to the set of real numbers. So here e is a set of experiment outcome. Okay, so random process or stochastic process is a rule that there we can say stochastic or random process is a rule that maps every outcome e of an experiment to a function x t e, where t is the time and e is a uh, experiment outcome, and x is any function. Here we can use f or h. This is just some notation, not necessarily x, but we can write another variable. So this function define the experiment outcome based on the on each scan or on the time. A random process is usually conceived of as a function of time, but there is no reason to not consider random process that are function of the of other independent variables such as special coordinates, but we usually use the time because they are it is time dependent. So the function is suppose the function is uv, so uv is the coordinates, this uv is a coordinate and e is the outcome. So outcome e is has a location of u and v. So this function would be a function whose value dependent on the location u and v and the outcome e, and that could be used in presenting random variations in an image. So suppose this is an example, and this figure shows that the function has some outcomes. This variant, this notation is called the variant, and the 1 2 3 k up to n outcomes from the experiment and based on the time t1 t2 and up to t. So these are random, not that have a similar shape. Time 0 have different shape, time 1 has different shape, time 2 has a different shape. So these are random shape, not same. So let variant denote the random outcome of an experiment. To every such outcome, suppose a waveform, this thing x of t comma this thing is assigned. The collection of such a waveform form a stochastic process. The set of this thing and the time index t can continuous or discrete, countably infinite or finite as well. For fixed, this will belong to the subset, or this is maybe the what we talk about overall the space, overall the space vector, and this ith measurement belongs to the S set of all experimental outcomes, and x of t comma this value is a special time function for, and for fixed time x1 equals to this thing where x1 has a function of t1 and this ith value is a random variable. Finally, if we sum up all the, if we look at all these things, is the family or ensemble of such a realization of this thing over time, which represent a stochastic process. Now the mean and or ensemble average of the random process. Here we calculate the mean value of the random process like this one. Okay, its autocorrelation is defined for real value scalar process as this one, and this is the autocovariance. So here the outcome, each outcome is multiplied with the periodic distribution of x as a function of time and integrated with the outcome. And autocorrelation, this thing autocorrelation of the same variable but is a function of t1 and t2, this one, and the autocovariance of two time t1 and t2 is equals to the difference of the mean of t1 and difference of the time mean difference of the mean at time t2, and is equals to this one. Then a stationary random process. So there are two kinds of stationary process. One is strict sense stationary, and another thing is wide sense. One is a strict sense that is not used in the tracking system, but in the tracking system we use the wide sense stationary uh, stochastic process for the random noise. So stationarity refers to the time invariance of some or all of the statistics of a random process, such as mean, autocorrelation, and total distribution. A random process whose mean is time invariant and whose autocorrelation is of the form below, this call is wide sense stationary. Okay, where the mean is time invariant and whose autocorrelation has a form of this thing. The R has a difference between T1 and T2. In this is actually time shifting tau equals to T1 minus T2. Autocorrelation of that variable T, that is the first two moments are invariant with respect to a shift of the time axis is called wide sense stationary or less rigorously stationary. The white noise uh, not necessarily stationary. It can be uh, random uh, or Gaussian noise whose autocovariance is 0 for any two different times is called white noise. Okay, so it has 0 mean and some covariance. Okay, so in this case suppose this is uh, autocovariance equals to, this is instantaneous variance. The sigma is instantaneous variance, and this function is impulse function. So we just this is same thing, we just replace s naught and s naught of t1. Okay, and this function is same, both same. You can write here this way. The above property is the white sense whiteness. So white noise has the autocorrelation this one and mean 0. So stationary 0 mean white process has the autocorrelation this thing. Okay, it is convenient in object tracking system to consider a stationary 0 mean white process in mathematical model. So we just mixed or add up uh, the 0 mean white process or white noise to the Gaussian model or the PDF Gaussian model in the tracking system. And Markov process. Markov processes are defined by the following Markov property, like this one. When it used for the distribution of x, where you already know the past values. Okay, you already know the past values, not the future value. You do not know the future value of the random variable x. So here tau uh, is less than t1. Tau is any shift of the time which is less than or equal to t1. So you can calculate the present value based on the past value, and this will equals to this thing, the same thing. P of x you can write this way and this way. That is the past up to any t1 time is fully characterized by the value of the process at t1. So at the t1 up to t1 you already know all previous history. So up to t1 you already calculated the history of the PDF of the x. So the future is independent of the past if the present is known. For example, the Vanier process is a Markov. This W is a Vanier process. This follows from the fact that it is the integral of the white noise. So it is actually integral of the white noise. uh, adapt with this thing um, with white noise, integral of white noise, and n of t is independent of uh, w, which means w and white noise are uncorrelated, and they are independent. So this white noise and the linear process w are independent. For example, the object state x of t of a possibly time varying dynamic system driving by a white noise n of t is a Markov process. Then the velocity of the object state is a function of time x of t and n of t. Okay, the velocity of the object state at time t1 is a function of the time, current time, and the object state having some white noise. So in general, both x of t and n of t are vector value random process. So, normally uh, we add white noise in the object state, and we add linear process. We add this w noise, in the sensor measurement. So sensor measurement means suppose sensor received measurement from the object. So when or you can say that the sensor noise. Okay, so you can say the linear process is the sensor noise which will added in the measurement of the sensor. Okay, whatever sensor receiving position and velocity, everything with whatever it is receiving from the object, it will add some measurement noise, uh, which is w, and the white noise is added with the object state like this one. Now random sequence, Markov sequences and Markov chain. So random sequence or a discrete time stochastic process is a time index sequence of a random variable. For example, radar generate random sequence of measurements such as this one. Okay, so is a complete set of measurement receiving in each scan from the radar. Okay, suppose radar generate measurement for the 80 scan, 80 scan, then this j start from 1 and end to 80. So this whole set is describe the random sequence of random variables, because radar generate random variables related to the space object, related to the object which are moving in the space. So radar generate random values in each scan xj start from initial scan and up to the end of this scan. And Markov sequence, suppose the object state x of t of a dynamic system excited by a noise v of k. So this is white noise is the object state is white noise is added in the object state x of k. Then what will be the next scan object state? This is called Markov sequence. Markov sequence means that the how object state is propagated for the next time scan. Okay, so x k plus 1 means if we are at k plus k equals to 1, then what will be the object state at 1 plus 1 2? What will be the x of 2 at time k1 and x of 1, and this v is actually white noise v of 1. So we normally denote the white noise by v in many tracking algorithms. So this system is a discrete time Markov process or Markov sequence. In general, both xk and vk are vector valued. So these are vector valued. The state of linear dynamic system excited by the white Gaussian noise, this thing. So how we calculate the x plus 1. We just calculate x plus 1 using the f of k. So f of k is a transition matrix which is used to calculate the transition of the x. Means it has some time valued matrix. When we multiply some time valued matrix with the x, it will calculate the uh, velocity, and velocity will be added to the x to give the x plus 1. So you can say this f of k is constant velocity model. So as you know, the constant is f is suppose fk is known as a constant velocity model. So as you know, constant velocity model, we just uh, uh, divide the uh, multiply the object state with the time. So when the distance is multiplied with the time, it will give you the velocity, and then velocity will be added to here the position, then it will give you the next position. So suppose x is 4 vector, means 2 position vector and 2 velocity vector. So suppose it is a 4 by 1 vector, x y, and x velocity, y velocity, and this is a 2 by 2 matrix. uh, uh, then no, it must be 4 by 4 matrix. It must be 4 by 4 matrix. So when it multiply, it will give you the next object state value, which is also a 4 by 1 vector. It will give you the next scan position and next scan velocity. So this equation is called a Gauss Markov sequence. Um, so it will sequentially find out the object trajectory which have white noise. So the reasons for this are as follows. Because of linearity, x of k is Gaussian. So assuming the initial condition is Gaussian, and because of whiteness of driving process noise, it is Markov. So this why it is called Gauss Markov. So where in this equation, where x becomes the integral sum of the white noise sequence term and is called a discrete time linear process. And here the time can be any value. Suppose not necessary the k is 1, 2, 3, and there is only 1 second difference between each scan. So in each scan there can be a uh, 0.1 second, okay, 0.5 second. This depend on the model, and this depend on the time is depend on the area, and uh, the number of scans, and overall how we follow up the Markov sequence to calculate the object trajectory. So here just we multiply the time and transition in the transition matrix with the object state. Markov chain is a special case of Markov sequence in which the state space is discrete and finite. This is a chain. This is a chain of object state. Okay. So the Markov chain is a special case of Markov sequence in which a state space is discrete and finite. Suppose x of k. So where k is equals to belongs to xi, and I equals to 1 over m. Okay, so k is a scan time and I is a measurement. So at scan number 1, or any scale like scale number 2. So x of 2 is have uh, have uh, have a chain of nth value of measurement. Okay, if in the current scale there are 5 measurements, then this bracket is having the argument like x1 comma x2 comma x3 and up to comma x5. So suppose there are 5 measurements selected in the current scan x of 2. So it is a chain. Okay, so it is chain of measurement related to the x of k. Its characterization its characterization is given in full of by transition probabilities. Transition probabilities actually uh, uh, maintain and update automatically using some Markov chain or Markov model formula, which uh, multiply the transition probabilities to the periodic probability of the object state in order to update the next scan probability. Okay, it means you already know the previous probability, so to automatically update and maintain the probability of p of x, the probability of target existence. Automatically you must know the previous uh, uh, value like x k minus 1 and some initial probabilities. So the probability of xk, the probability of a current scan xk equals to xj condition of x minus 1. Previous you have already known this value, and which is equals to x1, you already know. So this equals to the pi ij. This is a matrix where I and j equals to 1 over n. So here what we will do when tracking system initialize track, it is used to initialize the track using the sensor measurement, and each track is initialized with the initial probability. So every track has a known initial probability. Then when it arrive when we are updating the track, when we are updating each track, then we update the initial probability using some Markov chain matrix. So we multiply the Markov chain matrix with the current probability. Like this, for example, define the vector like this one. So this vector is actually probability of target existence, where the components are probabilities of the chain. So suppose the u1 is a probability of x1, and u2 of k is probability of the of x2, where x1 x2 are the measurement like this one xi, like this one xi. And so you have to first understand this thing. This xk is only the current scan, okay, object state, but in the current scan there are many measurements. So x belongs to x is related to many measurement, has a Markov chain measurement, so by where I equals 1 for n. So xk is uh, belong to a vector of measurement. All measurement are calculated or measured in the same scan. So in the same scan you have to calculate the probability of all value. So this is probability of u of k. So u of k, probability of u of k equals to probability of each measurement in the current scan k. So probability of the x1 and probability u1 u of 2 of belongs to the probability of x2 at the same scan, at the same current scan. So these components are probabilities of the chain being in state I. So ui of k is equals to probability of x of k equals xi. So each u is equals to is having a probability is having each u having a probability of x of k equals to xi. So this vector describes the PMF, the probability mass function or probability point function with the state of the chain. The evolution in time. Evolution means we are updating. How we update the probability this thing. The equation number 4. The evolution in time of above equation is then given by ui of k plus 1 means the probability of the object string for the next time scan is the sum of the this pi ji ui and ki. But ui is the sum of the probabilities and to some this transition matrix this we said pi ji the transition matrix we multiply transition matrix to update the object probability existence. It can be easily shown that above equation 5 can be written in vector form by the with the notation of equation number 3 like this one uk plus u of micro u of k plus 1 equals to product of u of k, where this thing is equals to the matrix is a transition matrix of the Markov chain. Okay, so what will be the value of the j I? Normally we select 0.98. It's always because this is probability transition matrix, so it cannot be higher than 1. It can be best selected uh, based on the getting probability. Getting probability is the when there are plenty of measurements in the current scan, then we select some window. We cannot calculate the plenty of measurement. If we calculate plenty of measurement, then the computational complexity will be access will access the available computational resources. So we cannot calculate the probability of plenty of measurements because radar generate plenty of measurements. There are so many measurements, even we cannot count the number of measurements. So just we select a small window at current scan where the target is moving with a constant velocity. So based on the maximum velocity of the target, we just select the window or get. So based on getting probability, this value is selected. So normally the getting probability is selected as a 0.99. So with the getting probability of 0.99, this product, this transition probability is selected as a 0.98. So this 0.98 is multiplied with the um, current scan object existence. So if we multiply the 0.98 and with this probability, it will update the probability of target is existent for the next time scan. So for the next time scan, we will use this value as a periodic probability of the target is existence. So this is periodic. In this scan, this u of j is a periodic object existence, and this is posterior object existence. So and when in the next time scan, this will come as a this will use as a periodic object existence in order to calculate the posterior object existence in the next time scan. So I hope this lecture is clear to you. Here, whatever we have is studied, everything everything will be used in the tracking system. So whatever we have discussed uh, is, is will be reused in the formulation of the tracking system. So you have to repeat this week lecture the previous lecture and this lecture, repeat everything. And when we start to study about estimation in the next week, and in the future when we develop the tracking system, then the same thing will be employed. So you have to discuss uh, with your class fellow and try to understand the previous lecture and this lecture, and these two lecture I follow up the fundamental of object tracking. So you can follow the object tracking book. I have given the soft copy of the fundamental of the object tracking book to one of the student, so you can share the book, and in meanwhile you can discuss, and we will meet in the next class. I hope we can meet in the next class on the Tuesday. So bye. Okay, thank you.